Thank you very much. Thank you very much for the invitation to this very nice workshop. I'm enjoying it a lot. And well, I'm happy to tell you a bit about our research. So this is concretely, this talk is based, as I've written down here, on our recent preprint, which is joint work together with Chris Fewster and Ian Jupp, both of which you have heard today already. So yeah, this talk is about observing observables. And the idea is that the way I want to talk about observing observables is in terms of measurement schemes. And because Ian has just told us that whenever you talk about the measurements, and in particular, whenever you talk about update maps, you have to be very careful about causality. So I will tell you about causal measurement schemes. And in particular for every observable of the linear real scalar field in curved spacetime. So let's get started. Oh, can you see this? So this is an outline of my talk. So first of all, I give you a quick reminder of what measurement schemes are, reminding you of what you've already heard in Chris's talk. Then I'd like to set the stage and describe the task that I have set ourselves here. Then I'm going to tell you the result. I'm going to tell you a little bit about the proof idea, what's behind all of this, and I'll conclude with a summary and an outlook. So good, let's get started. So a quick reminder about measurement schemes. So what is the objective of a measurement scheme? How do we describe measurement using measurement schemes? The objective is we want to analyze how information about one physical structure, that's called the system, is transferred to another physical structure called the probe that is controlled by an external experimenter. And to give you a little more motivation for this, I've just copied here this paragraph from the book Quantum Measurement, which goes as follows. So the quantum theory of measurement is considering measurements as physical processes subject to the laws of quantum mechanics. Here we identify a hierarchy of 3 levels of description. We have observables, instruments, and measurements. And this hierarchy reflects the options of restricting one's attention to the outcome probabilities at the level of the measured system, being the observable level, or taking into account the system's conditional state changes. This is taking into account, or this is called the instrument level, or adopting the most comprehensive level of modeling, the interaction and information transfer between system and probe. And this is precisely what we are doing. Okay, so to summarize the working assumptions and to be very clear what it is that we are doing is, we assume that we have a fixed external background and external observers here, right? So this doesn't go anywhere near the idea of quantum gravity, where you would suppose to have, well, background independence or something like that. Furthermore, we assume that we have a clear cut between a system and the probe. We can distinguish them very clearly. Third, we assume that our observers are in full control of their probe, right? They can prepare them, they can post-process them, and also, this is part of the assumption here, we assume that we can measure them, which means that we assume that the extraction of classical information from the probe is known, right? So all of these assumptions are the basic working assumptions of a measurement scheme. Good. Okay, now let me set the stage, okay? So let me tell you the setup, the task of today's talk. A setup is we assume that there is a globally hyperbolic space-time M with a linear real scalar system field, phi s, okay? And we have an external observer with access to some probe quantum field who, let's say, is granted full control over the probe and the system in this region N here that I've drawn. And moreover, we grant this observer control in region L over the probe for post-processing of the probe. Okay, so that is the idea. And now the task is the following. Okay, for a given system observable A in N, we want to find a probe field with some initial state and a coupling of the probe to the system within this region N, and a probe observable B in the post-processing region L, such that for every system state, equation number 1, this equality holds. Okay, so let's see what that means. On the left-hand side, we have the expectation value of our system observable of interest in the initial, well, system state. And on the right-hand side, we have the expectation value of, well, the identity on the system and our probe observable. Then we have here a scattering map that takes into account the coupling, the interaction between the system and the probe in region L. And then we have the bipartite state of the system and the probe. So on the right-hand side, basically, we keep in mind that there is a system and a probe and that there are both. And on the left-hand side, we say, well, we're just interested in the expectation value of the observable A. Okay, so in other words, this should remind you basically of Chris's talk, which is here just written in a more usual, let's say, Hilbert space picture with density matrices and traces, and not in the more abstract way, as we've also seen in yesterday's talk by Robert Wald and also in Chris's talk, in the more abstract algebraic picture. So what this equality here tells us is basically we're looking for a collection of things such that A is the induced system observable of the measurement scheme consisting of the probe theory, initial probe state, and probe observable B, and some scattering operator that comes from coupling. Okay, and again, the idea is that this B, this probe observable, lives in L, where the observer does the post-processing of the probe, looks at the probe, whatever, and the scattering map comes from the coupling within N. Good. So now, having told you the task, let me skip right to the result at this point. This is the following theorem, which is in our preprint. So the theorem is as follows. For every observable A of a linear real scalar field, local to N, so local in here, there exists a collection of Fewster-Verch measurement schemes. So there exists a whole collection here with index alpha, each with, well, processing region L, which basically means that all these B alphas are local to L, and coupling in N, okay, and which basically means that this scattering map here, this S alpha, comes from a coupling within N, and by the name Fewster-Verch measurement scheme, I'm basically saying that this coupling, that this scattering operator here comes from a coupling in the sense of the one that you've seen in Chris's talk. So it's a local coupling in particular that respects the rules of locality and causality. Good. So we have this bunch, this collection of measurement schemes such that the induced observables of those measurement schemes, right? So we get a bunch of induced observables, they converge to A. So the idea is that we do not get a single measurement scheme for A, but we can do almost as well as that, in a sense that we can get a collection of measurement schemes such that the induced observables converge to A. And this collection then is called an asymptotic measurement scheme for A, with coupling in N and processing region L. So if you want, this is, I'd like to think of this as something very operational, in a sense that, you know, someone comes to you and tells you, okay, can you measure A? Can you build an apparatus? Can you build, theoretician would say, a measurement scheme that measures this A? And then I come up with, well, one element in this collection and tell you, this works pretty well. It measures A up to some error epsilon. And if you want it even better, then I can build an even better apparatus that can measure A even closer with even smaller error margins. So in that sense, I would say that, well, this has also a very nice operational interpretation, this collection of measurement scheme. And well, yeah, this collection is an asymptotic measurement scheme, we say. Now, for the experts in the audience, maybe some terms and condition. So this convergence holds inclusively but not exclusively in the strong operator topology of representations of quasi-free state with distributional two-point function. So why do I tell you this? Basically, you might ask, what does it mean that you converge to A, right? Okay, good. So the topology is as explained, and in particular, it's a very useful and very natural one, so to speak. Good. In my remaining few minutes, I would like to give you a proof idea, and for that I have some preliminaries here. So first of all, what are the observables of a scalar field? So I think we've heard this already also yesterday in Robert Wall's talk, and today also in Chris' talk, and Ian also talked quickly about this, but just as a reminder. So let's say we have S phi equals 0, the equation of motion could be, for instance, Klein-Gordon, then S would be, right, box plus minus m squared, something like that. Then we have the observables. What are those? Well, those are then generated by those smeared fields. And as Ian said in the last talk, basically, if you come from this picture where you think of phi of x as the field, you basically smear this out against a completely supported smooth real value test function. But you can also do this more general. You can think of those as abstractly generated objects. They generate some algebra, and in particular, they then fulfill those 4 conditions, right? Where the first one is basically just some linearity. The second condition tells you that we're talking about a real scalar field. The third condition is, well, this is a field that fulfills the equations of motion. And the fourth one is the canonical commutation relation. Good, so this is our system theory, our system field. And now remember the task. What do we want to find? We want to find measurement schemes for that. In particular, we need to find a probe theory and we need to find a coupling. And let's do the easiest thing we can think of. A probe field, let's also take a linear real scalar field, possibly with some different equations of motion. Let's call it phi p. And now we also want to find a coupling. And this coupling is very familiar because it's also the one that you've seen in Chris's talk. And it's basically the easiest coupling that you could write down to keep the system bilinear, so still solvable, still quantizable, non-perturbatively, so to speak. And the corresponding interaction action would be given by this guy here. So what do we have? We have lambda, some coupling constant. We have k, some, think of it as an external field, some completely supported coupling function that confines the coupling to a compact region, and then we have just this bilinear term phi s, phi p. And again, this k is a completely supported coupling function with support in n. Okay, good. So this is a class of models that we now have, a class of couplings, and let's see what we can get. Okay, and this is the next slide. And let's see what do we get in the case where our desired system observable A is just a smeared system field, phi s of f, okay? Let's see what we get. Remember that as part of the measurement scheme that we want to find, we now also need to specify some initial probe state and a probe observable. And if you play around a little bit, then you make the following observation. For any state, for any probe state, rho p, and for the following probe observable, b lambda, being phi p of lambda to the minus 1h minus some explicitly known constants, c lambda times the identity, okay, for any observable that looks like this, okay, where h, let's say, is a compactly supported test function with support in the region L, such that this whole observable here is in the region L. The observable, the induced observable of this guy here is phi s of minus k, the coupling function applied to this green operator acting on H plus higher order terms. And now this is nice because what this tells you is that if you now just take the coupling constant lambda to 0, what you get is you get phi s of minus k EP minus H. Okay. And if you think, well, where is this localized? Well, because of you multiply by this k here and this k had support in n, this guy lives in here. Okay. So now we have an asymptotic measurement scheme. Asymptotic because we need to take lambda to 0. We have an asymptotic measurement scheme for phi s smeared against this guy here. But our objective was phi s smeared against a function f, where f has support in n. Now the cool thing is that because of the degrees of freedom that you have in this model, you can find a suitable k and you can find a suitable h such that phi s smeared against minus k EP minus H is actually phi s smeared against f. Okay, so this is just some technical stuff. You need to do it, but you can do it. And in summary, basically, what we see is that if we take as a probe theory, a linear real scalar probe field, any initial probe state, then we take the following probe observable here, and we take the coupling that we get from the interaction action on the previous slide. We get an asymptotic measurement scheme for one smeared field with coupling in N and processing region L. So we have completed the task for a single smeared field. What about the general case where we have maybe a product of smeared fields or even a linear combination of product of smeared fields? You know, Ian basically showed in the last talk an example of a general element of the local algebra. What happens if you take one of those self-adjoint elements? Well, I just leave this as an exercise to the listener. And what you can do is you can use multilinear polarization identity and more probe fields. And for details, you could have a look at our preprint. And with this, let me summarize and conclude. So in summary, FV measurement schemes, Fewster-Verch measurement schemes describe information transfer from a system field to a probe field via localized coupling. The resulting maps are causal state updates, which is something that Chris told you about. And as you could infer from Ian's talk, those will typically not be ideal measurements, but nevertheless, if you specify a coupling, if you specify an initial probe state, if you specify a probe observable, you get those update maps. You just need to tell me how you measure in order to get them, but this is nothing bad. I've shown you that explicit asymptotic FV measurement schemes exist for every observable of the linear real scalar field. May it be the field algebra that I've shown you. You can also go to the Weil algebra. You can go to the von Neumann algebra. Everything is covered. And this would be evidence, though not the proof, but evidence that fully causal measurements for every QFT observable exist and can be modeled by FV measurement schemes. And maybe just to give you a quick outlook, of course, it would be interesting to extend this to those non-linear observables that also Robert Wolf talked about. So weak ordered product, stress energy tensor, and something like that. But this is left for future work. And with that, I would like to thank you for your attention. And I'm happy to discuss and take questions.